Hello and welcome to my video, lesson 9.4 on trig identities. And we're talking about today the double angle identities. So there's three different double angle identities. This is the sine, cos, and tan double identities that we're looking at today. And there are three versions of them, like one for each, sine, cos, and tan. And so those ones, I'm not going to try to prove those, just accept that they exist and we'll move on. But cos could also be changed into one of these two versions as well. So if we take this cos identity and we use the Pythagorean identity, that is sine squared alpha plus cos squared alpha equals 1, and then we rearrange it for whichever version we want. So if we go like this, sine squared alpha equals 1 minus cos squared alpha. Or we do the other version, which is cos squared alpha equals 1 minus sine squared alpha. So those are the two versions of the Pythagorean identity. And we take those and we plug them into this blue equation here, this original cos double angle identity. Then what we can do is get these other versions. And so if we plug in, instead of writing sine, we plug in this green equation, then what we get is cos squared alpha minus the sine, but the sine is 1 minus cos squared alpha. And if you multiply that out, you get that statement because there's two positive cos squared alphas and a minus 1. Okay, and if you do the same thing here, but we do this for the cos, we get 1 minus sine squared alpha, and then a minus sine squared alpha. And so you can see how, again, that simplifies to this version right here. So these two are really coming from the original there, cos to alpha version. So if I were giving you the equations, I would not give these two on your formula sheet because those are just the same as the original, but from Pythagoras. But that being said, all 5 of these are on your Alberta diploma formula sheet. And so hopefully you can just pick the one that matches the question best. If you pick the wrong cos version, you just use Pythagoras to move over to the correct one at a later time. Okay, so just like with the last lesson with sum and difference identities, this is especially helpful because it lets us solve angles that are not on the unit circle. So first, we're going to do a couple questions that are not on the unit circle. So here we have cos squared pi over 8 minus sine squared pi over 8. Well, all we have to do is plug this into the cos double angle. So this is cos 2 times the angle, which is pi over 8. And so once we do that, it's cos pi over 4, and that's on our unit circle, so it's root 2 over 2. Okay, and so we can find exact values to other expressions. So this expression here did not have a unit circle number angle, but it was solvable. Okay, in the same way we can do that for this one. The problem is this one looks a little bit different. So if you pause the video now and try this out yourself and see if you get the same answer I do. Okay, so like I said, this one looks a little different because it doesn't match any of our double angle identities. It is similar, but does not match this one, the sine 2 option. So sine double angle option, 2 alpha option. It's similar to this, but it's not quite what this says. Why is it not the same? Because it has this 2 here. So what we need to do is just divide that 2 across the equal sign. So this is now sine 2 alpha over 2 equals sine alpha cos alpha, and now it actually works. So now we can take this, which is this, and we can replace it. So we can replace this statement with sine 2 times 15 over 2. Okay, so when we do this, we get sine of 30 over 2. And what is sine of 30? Well, 30 is the shorter of the two triangles, so it is 1/2 divided by 2. So the answer is 1/4, and that is our final answer. So this is helpful to solve situations when the angles are not on the unit circle. But let's go ahead and continue by proving some identities. So we've got 4 different identities we're going to try to prove in this lesson, in this video. Every identity is going to be slightly different. Every different proof is going to be slightly different. But you just got to go through the process and try your best, following to look for some patterns. So what we're going to do here is expand out the right side. So we're going to have sine squared theta plus 2 sine theta cos theta plus cos squared theta. So this is just a perfect square trinomial. You can FOIL it out and show the work a little bit more carefully, or you can just do what I did if you're comfortable with it. This is 1 plus, and then this is a double angle sine. So this is 2 sine theta cos theta. Okay, so we've done one step on each, but we're not quite done yet. What we're going to do, the left side we're going to leave as is, but the right side we're going to notice that these two together are our Pythagorean identity, which is 1. If you add those two together, we get 1. So it's 1 plus 2 sine theta cos theta. And so now we can say left side equals right side. So we have done our proof. Okay, let's take a look at our next identity and proof. I recommend you pause the video now and see if you can solve this one. Okay, if you are able to solve this, then you press play and you see what I got. So here we're going to change this from secant to cosine, and then it's 1 over. And then the right side, let's get rid of the double angle. So, which is going to be better to choose? I'm going to guess it's going to be the cos one, because I can see that there's a cos squared. And so I'm going to try for the cos one that has cos squared. So this one here. So 2 cos squared theta, and then I think it's plus 1. Let's just check that. No, minus 1. Yes, and that's going to be important because once we have that, we can cancel out these two guys, and so we can write 2 over 2 cos squared theta, and the nice thing is we can cancel those guys out, so we're 1 over cos squared theta, and now we can say left side equals right side. Okay, here's another one to try. See if this one works for you. Pause the video now and see if you get the same result I do. Okay, so always when I see a secant, I am changing that. So this is going to be negative 1 over cos 2 theta. I'm going to leave it like that for now. I'm going to look at the left side. Even though this has the double angle, I'm not sure which version it's going to be. But on the left side, I can see actually, you know what? I can see a pattern already. This part here can change into, this is just a Pythagorean identity. It's going to be 1 over, and then the bottom is going to be the cos 2 theta. So you know what? We're not even going to do that. We're going to do it on the left side. So this is cos 2 theta. And this is, again, the identity Is it? Oh, you know what? I think I've done something wrong. This is cos minus sine. This is sine minus cos. Oh no, what have I done? Okay, so what we're actually going to do instead is we're going to take out a greatest common factor of -1, sorry. And that allows us to rearrange this. And now we can actually get our answer. So it's going to be -1 on top, and then we have the cos 2 theta on the bottom. And now we can say left side equals right side. All right, you can pause the video now and try this for yourself and see if you get the same answer I do. Okay, so on the right side, it's pretty obvious. We're going to get 2 sine x cos x minus sine x. And now we can take out a GCF, a greatest common factor of sine x. And so we get 2 cos x minus 1 inside the brackets. On the left side, we can take out a greatest common factor of sine x. And we can make it cos 2x plus cos x. On the denominator, it's cos x plus 1. Then what we can do is take that double angle identity for cos, but we're going to use the version that is 2 cos squared x and a -1, but we're going to put the cos x and then the -1. And the reason is because now it's in the form of a quadratic, which means we can do PSA 2 on it. So we're going to keep everything else the same, but we're going to have the numerator have that PSA 2 statement. So it's going to be 2 cos x, and on the other side it's going to be cos x, and then one side is going to be minus, one side is going to be plus, and we need to get a 1, so it's got to be 1, 1. The question is which side is positive? Well, the bigger side, because this, if you multiply, gets the positive 2 cos x, and so we get that middle term. Please go ahead and actually do PSA 2, or go back and watch some of my Math 10C videos if you don't remember how to do that. Okay, so now that we have this, we can see something wonderful happen. These two cancel. And so finally, our statement is sine x 2 cos x minus 1, which matches with the other side. So left side equals right side. Okay, and one more question, just bonus here. One more question to try. This shouldn't be as hard as the last one. Just wanted to add one extra. But pause the video now, see if you can do it yourself. Okay, now when I'm doing this one, I'm noticing that the right side just has sine squared theta. So that's how I know that I want to pick 1 minus sine squared theta as my double angle identity version. I can just double check that that is correct though. Yes, minus 2. Oh, I forgot a 2 here. Minus 2 sine squared theta. So just double check that that's correct in your formula sheet. But once you have it, now we can write it out. So it's 1 minus 1, double minus, which gets plus 2 like this. And then hopefully you can see that these ones cancel. And so then we have 2 sine squared theta over 2. These two cancel. And so we're left with sine squared theta, which means left side equals right side. All right. I hope this video helped you better understand, especially proofs, but specifically with all of our double angle identities. Hope it helped, and good luck.